Good morning. Myself, Dr. Suparna Rana, serving as Associate Professor in Haldia Institute of Technology, West Bengal. Today I discuss on the second part of the stereochemistry. Now first I am telling that chirality. What do you mean by chirality? Chirality, the term is coming from the Greek word chair, means hand, and from here it is coming that handedness relationship, means if I take here, that is my left hand and this is my right hand, so that right hand and left hand, their relationship, they are non-superimposable mirror image. As I am telling it in my first lecture, so I am just telling here, if I take one mirror, so therefore that is a mirror image to each other. Now if I want to superimpose to there, so they are not superimposed to each other. So we can say that left hand and right hand, their relationship, they are chiral and they are not generates that the non-superimposable mirror image. Now here I am telling one thing, that another term known as the achiral. Achiral means they are mirror image but they are superimposed to each other. Say for example, if I take that the chair and its mirror image, that the another chair, and if I superimpose to each other, therefore they are superimposable. As they are superimposable, so we can say they are achiral. Now chiral carbon atom means if the carbon atom linked with the 4 different groups, so there are 4 groups, so we can say this is the chiral carbon atom. Say here this is our 1, 2, 3, 4, so therefore we can represent in this, so we can say this is the chiral carbon atom and its mirror image, so therefore it will generate that its mirror image, so they are also that generates that the non-superimposable mirror image compound. As they are generates that the non-superimposable mirror image compound, and we can say they are enantiomer and they are, we are telling that individually they are optically active compound. Now achiral compound means carbon linked with the 3 different groups and another one is the same, or it is 2 different groups, or it is that the 4 groups are same. Therefore we can say this carbon is the achiral carbon. Now stereoisomers, compounds with the same connectivity but different arrangement in space, we can say they are stereoisomers. And another thing that stereoisomers, they generate that the non-superimposable mirror image, so we can say they are enantiomer. And if they are that the no mirror image relationship of these 2 isomers, we can say they are diastereomer. And the compounds having the 4 different groups with the attached with the carbon atom, so therefore we can say this is the asymmetric center or asymmetric carbon atom. And if it rotates the plane polarized light by some angle, so therefore we can say the compound is optically active. And is this the one of the property, physical property of this compound, that its optical rotation and how much it rotates the plane polarized light, and this is the physical property of this compound. Now the chiral compounds, a compound which is optically active and but will not rotate the light, so therefore we can say that it is the achiral compound. And another term, that the polarimeter. What is a polarimeter? Polarimeter is a device that measures the optical rotation of the compound. We cannot say the compound's optical rotation to see the structure, to write the structure. We can only measure when we measure by the instrument, that is known as the polarimeter, then we can say what is the optical rotation of this compound. Now we are telling about the polarimeter. Polarimeter, it is nothing but it is the composition of the 2 things. One is the polarizer, another is the analyzer, and that is nothing but it is a combination of the 2 prism. They are combined to each other, and here in the polarimeter there is the 2 prism. They are joined by a glue, and this is known as the balsam glue, Canada balsam glue, and when they are joined, so they generate a polarizing filter. And another thing that another is the analyzer, that is another two prism, they will combine, and with the help of the glue, that is the Canada balsam glue, they generate that the analyzer, and they analyze how much rotate this one. So therefore these two prisms, combination of the prism, they are present, and the prism cutting edge is 68 degree, and here it is used. Now here it is a sodium lamp, and it is coming that is generates that the monochromatic light when it is passing via the polarizer, and this is the monochromatic light, and here we take that the sample solution, and this is when it is going via this sample solution, and it will rotate some angle, and that rotation is analyzed by the analyzing filter, and we can see by our eye, that is the detector will show that how much angle of rotation is taking place. Now the angle of rotation is two types. One is known as the clockwise rotation, another is known as the counterclockwise rotation. If it rotates the plane polarized light by the positive rotation or clockwise rotation, we can say the compound is dextrorotatory, and we can denote it by the compound by the small d or plus like this. Okay, we can say they are the dextrorotatory compound. And if we rotate by some angle, that is the counterclockwise or negative rotation, we can say the compound is the levorotatory, and we can denote it by the small l or it is negative sign. Now how we can determine that the specific rotation of the compound? So we can represent that the specific rotation alpha Td. What is the T? T means in which temperature we measure the optical rotation. So that is the T in degree centigrade, we can put here, and lambda, that is the wavelength of the sodium D light, and it is say 589 nanometer, and is equal to, that is 100 into alpha divided by L into C. What is the alpha? Alpha is the degree of rotation which we can measure by the polarimeter, and L is the length of the sample tube, and C is the concentration of the sample tube. Now length of the sample tube, that is in decimeter, and the concentration of the sample, that is in gram per ml. So therefore we can represent that the specific rotation alpha Tt is equal to 100 alpha divided by Lc. In this method we can determine what is the compound's specific rotation. Now from this specific rotation, we can say that the compound is optically active or inactive, or any other thing we can see from here. Now that is the thing we are discussing. Next one, that the angle of rotation depends upon the various types of factor. Now from this equation you can see that alpha Td is equal to that 100 alpha divided by L into C. So it first depends on the nature of the compound. Secondly, it depends on the nature of the solvent. Thirdly, it depends on the concentration of the solution, and then it depends on the wavelength of the light used. And the fourth one, that is depends on the wavelength of the light used, and the fifth one, that the length of the solution column, and the last one, that also depends on the temperature. Now optically active substance classified into the two types. One is known as the dextrorotatory substance, another is known as the levorotatory substance. That substance which rotates the plane polarized light by the positive rotation or clockwise rotation, we can say that this is the dextrorotatory. We can represent by the small d or positive, and the levorotatory substance, that substance which rotates the plane polarized light by the counterclockwise or anticlockwise or left-handed, we can say this is the levorotatory, and we can represent by the small l or negative sign. That first we are coming that various types of compound, they are optically active or inactive. We can say from measuring the optical rotation, or that the when we put the sample solution into the plane polarized light, then we can say that compounds is optically active or inactive. But also, if I see the structure of the compound, from here we can say that the compound is optically active or inactive. That's why we can consider that the element of symmetry present into the molecule. So that's why we are discussing here that the four types of element of symmetry. So the first one, that is the rotational axis of symmetry, that it does not, that the optical activity does not depends on the rotational axis of symmetry. But at first that we are telling that which types of symmetry is present into this molecule. Say for example that if I take the water molecule, if I rotate the molecule by 180 degree, so therefore it generates that a molecule that is the same molecule. So therefore we can say any molecule which rotates some angle, after the rotation, if it generates the same molecule, we can say the compound has the rotational axis of symmetry, and by the we can denote it by the Cn. Now what is the n? N is the fold, and how can you determine that the n is equal to the 360 divided by theta? Theta, what is theta? Theta is the angle of rotation. Means here for the water molecule, if I rotate the 180 degree, then it will generate the same molecule. So therefore theta is equal to here 180 degree, as it is theta 180 degree. So therefore what is the n? N is equal to 2. So we can say that water molecule has C2 symmetry is present, or we can say that the molecule has two-fold rotational axis of symmetry. And in the same manner, that ammonia molecule, if I rotate the ammonia molecule by the 120 degrees, so therefore it will generate that the same molecule. So therefore that theta is equal to 120 degree and n is equal to 360 divided by 120, that is equal to 3. So we can say that ammonia molecule has three-fold rotational axis of symmetry, or we can say the molecule has C3 symmetry is present. Now we are coming to the plane of symmetry. The plane of symmetry is an imaginary plane that bisects a molecule in such a way that one half is the mirror image to the other. So therefore we can say the molecule has a plane of symmetry is present. If the plane of symmetry present into the molecule, we can say that the molecule is optically inactive. Why? We can say we are discussing later, but here I am just telling that if the molecule has plane of symmetry is present, the molecule is optically inactive. Say for example here we are telling that that it is generates that the mirror image, and here this mirror image is superimposed. As it generates that the superimposed, we can say the molecule has the symmetry is present, and here it is plane of symmetry is present. Now here A, if I divide here, means if I take one mirror, so that the, or we can write here that the imaginary plane if I represent, so therefore one half is the mirror to the other. So therefore we can say the molecule that the A has the plane of symmetry is present. In the same manner that we are taking the various types of compound, now this is the imaginary plane that bisects the molecule in such a way that one half is the mirror image to the other. So therefore these compounds has the plane of symmetry present, and these compounds are optically inactive. Next one, that is the center of symmetry, and we can represent by the eye. And the center of symmetry is the point that the imaginary point that equal part of the molecule is if I join, so therefore that is passing through this center, and we can say this imaginary center is known as the center of symmetry and is present into the molecule. So here I am taking one compound that is 2,4 dimethyl cyclobutane 1,3-dicarboxylic acid, and here we are considering this is our imaginary center. Now if I add these things, so therefore here to here the distance, and here to here this distance is same. As they are same, so we can say, and here also if you join, so this is passing through this center, all the lines are passing through this center, and the distance of these two groups, they are always same. So therefore this is our imaginary center, and we can say the compound has center of symmetry is present, and we can denote it by the eye. Next one, that is the alternative axis of symmetry, or we can denote it by the SN. And here N is the fold I am telling at first, and here also I am telling that here also, that is the N-fold alternative axis of symmetry is present into the molecule if the molecule is rotated some angle. After that, the in which direction it will rotate on that perpendicular mode. If I take a mirror and then we take the mirror image, and if the mirror image and the original compound, if it is same, so we can say the compound has alternative axis of symmetry is present. Now here I take this compound and we rotate the molecule into the 90 degree in this axis, on that axis, therefore it will generate this one. And as I rotate in this direction, so therefore we take the mirror perpendicular mode and it will generate that the mirror image, and this mirror image and the original compound, they are same. As they are same, so therefore we can say the compound has alternative axis of symmetry is present. Now here n is the fold, so as it is fold, so must be that angle of rotation is there. So here angle of rotation here, that is 90 degree. As it is 90 degree, so the n is equal to 360 divided by 90, it is 4. So we can say that the compound has 4-fold alternative axis of symmetry. Now we are taking the various types of compound. Say here this compound, it has the center of symmetry. Now center of symmetry is equivalent to 2-fold alternative axis of symmetry. Means if I rotate this molecule by 180 degree, then I take the mirror image and it will generate that the same molecule. So we can say that this molecule has that the 2-fold alternative axis of symmetry. And it has also the center of symmetry is also present, and we can say in other word that center of symmetry I is equal to S2, means that center of symmetry is equal to 2-fold alternative axis of symmetry. And in the same manner, the plane of symmetry is also represented by the 1-fold alternative axis of symmetry. Means if I rotate the molecule by 360 degree, then I take the mirror image, and therefore the mirror image and the original compound, they are same. As they are same, so we can say the molecule has the plane of symmetry is present, and we can say that alternative axis of symmetry is present. Now therefore we can say here as the 360 degree rotation, so therefore n is equal to 1. So therefore plane of symmetry sigma is equal to S1, or we can say that plane of symmetry is equal to 1-fold alternative axis of symmetry. Now here I am taking that the two terms, one is the asymmetric molecule, another is the disymmetric molecule. Any compound which have no plane of symmetry is present, center of symmetry is also absent, alternative axis of symmetry is also absent, or the simple axis of symmetry is also absent. Therefore we can say the molecule is asymmetric and the molecule is optically active. Okay, and the disymmetric molecules means plane of symmetry absent, center of symmetry absent, alternative axis of symmetry absent, only the simple axis of symmetry present. So therefore as these three symmetry is absent, so disymmetric molecule is also optically active. Okay, so asymmetric molecule, disymmetric molecule, both are optically active. Now how many types of isomer, possible isomer is present into the molecule? Say for example, now I am telling that if any compound which has the 4 different groups is present into the molecule, we can say this is the chiral compound. Now if the number of chiral carbon atom, if it is n, and the molecule has no plane of symmetry is present, so therefore we can say that it is a AB type or ABC type. Okay, now n number of chiral center is present. So therefore number of optically active isomer, that is equal to 2n, and the meso or the inactive form, that is equal to 0. So that's why that this compound is only one chiral center. Okay, n is equal to 1 and 2 to the power n is equal to 2 to the power 1 is equal to 2. So these molecules generates that the these two isomer, they are optically active isomer. Okay, no inactive isomer can be generated for these types of compound if this compound has no symmetry present. Okay, now if I take here that this compound, okay, this compound has two chiral center, one is this one, another is this one, but this compound has plane of symmetry is present. If you represent here that plane of symmetry is present, so one half is the mirror image to this one, so therefore we can say this is AA type compound. Okay. Okay, as it is AA type compound and number of chiral carbon, that is N, is equal to 2, and here it is 2 is the even number. So therefore number of optically active form, that is equal to 2 to the power N minus 1, means that is 2 to the power 2 minus 1, that is 2 to the power 1, that is equal to 2. So number of active form, that is equal to 2, and inactive form, that is equal to 2 to the power 0, means 1. So this isomer which has the plane of symmetry is present. So this is the, we can say this compound is the meso compound, we have described later, but this compound is the meso compound and this compound is optically inactive. This compound is optically inactive. And the another compound I am taking here, this compound, okay, this is the another isomer and this is the active form, and it has no plane of symmetry, no center of symmetry, nothing symmetry is present in this molecule. So therefore this isomer is optically active, and as it is active, so its mirror image is generated, so it is another active compound. So therefore if it is the 2 chiral carbon is present and molecule has the symmetry is present, so therefore here one compound, that is the meso compound I am telling, that is optically inactive, another compound optically active and its mirror image generates, that is also active. So here 2 active compounds and another inactive compound is generated. Now here if it is N is the odd number, therefore the optically active form is equal to 2 to the power N minus 1 minus 2 to the power N minus 1 by 2, and the meso compound, that is 2 to the power N minus 1 by 2. Okay. Now come to the next one. Now enantiomer. Okay, I am telling here that 2 compounds, they are generate that the non-superimposable mirror image relationship, and we can say they are meso compound. Say here also these 2 compounds they are enantiomer. Okay, so these 2 compounds, they are enantiomer. Okay, now here that the chirality is the necessary and sufficient condition for existence of the enantiomer. If it is not chiral, how it generates is non-superimposable mirror image? So therefore, as it is the chiral, so therefore if it is, then if it generates the non-superimposable mirror image compound, so we can say they are enantiomer. So these 2 compounds are enantiomer. Okay, and in this manner, these 2 compounds, they are also enantiomer. Mirror image relationship and non-superimposable mirror. Now here we are taking that the another compound, that it has the 2 chiral carbon atom here and here, but these 2 chiral carbon atom, they are not divided into the 2 equal halves, means it has no symmetry is present. So therefore it generates that the 2 to the power 2 means 4 optically active form. Now I draw here that the 4 optically active form, that is A, B, C, D. Okay, and A and B, their relationship is the mirror image relationship, and they are non-superimposable mirror image. As they are non-superimposable mirror image, so they are enantiomer. And the C and D also, they are non-superimposable mirror image relationship, so they are enantiomer. Now what is the relation of A and C or A and D? There is the no relation of the mirror image relationship, so we are telling they are diastereomer, means AC, AD, BC, BD, they are diastereomer. Now we are coming to the internal compensation. I am telling this thing that meso compound, this compound I am telling the meso compound. Okay. Now here if I take one mirror, so therefore this is the mirror image to this one. Now when we are taking this one, that the optical rotation, so any compounds and this mirror image, when we are taking the optical rotation, therefore it was observed that their optical rotation value is same but in opposite value. Means if it is D plus X, therefore that the mirror image compound is rotation is minus X. Okay. So if here also, that is one part is the mirror image to this one. So if this portion optical rotation is say plus X, this is minus X. So the total optical rotation becomes 0 and this compound is optically inactive, and it is due to the internal compensation of the optical rotation. So meso compound, it is optically inactive due to the internal compensation of the optical rotation take place into the molecule. Now external compensation means these 2 compounds, if I can consider this optical rotation is plus X, So its mirror image is this one. So its optical rotation is -x. Now if I mix that the 50% this one and 50% this one, means equal mixture of these two mixture, equal concentration of these two mixture, 50-50%, therefore their optical rotation becomes 0. And we can say that due to the external compensation of these two compounds, their optical rotation becomes 0, and we can say this mixture known as the racemic mixture, and due to the external compensation of their optical rotation, these two compounds are optically, mixture of these two compounds are optically inactive. So here also that is the D-tartaric acid and L-tartaric acid. If it is these two compounds mixture, that generates the racemic compound, and due to the 50-50% of these two compounds, it will generate that the optical rotation becomes 0, and the mesotartaric acid, due to the internal compensation, as a whole this molecule is optically inactive. Now this one is the meso compound I am telling, and the compound is optically inactive, and it is the compound has the I, sigma and Sn is present, that the symmetry is present, that's why the molecule is optically inactive. And this is the 50-50% mixture of these two compounds. We can say this is the racemic mixture, and due to the external compensation of these two compounds, the racemic mixture are optically inactive. Thank you.